Okay, so we've learned what the big three units of measurement are. We have length in meters, we have time in seconds, and we have mass in kilograms. So everything should be converted into that. I want to go over what's called derived units real quick, because we can get all of our other different units from these three that we're going to use in this class. So a derived unit, you've seen these before, you just might not have seen the name. An example of this would be something like density. And we give that a rho usually. And density is equal to how much mass per unit volume. So we can, for volume, we can do a meter cubed or a liter if we wanted to, right? So in this case, let's do the meter. Let's keep it in our standard units. So what we get is rho is equal to a kilogram per meter cubed. This right here is a derived unit. Another example of a derived unit, which we're going to get into, is velocity or speed. Velocity has units of meters per second. Alright, we can go one step further, and I'll show you this, but to do that we would take a derivative, a time derivative, and to get to acceleration from position we would have to take two time derivatives, and we would get a derived unit of meters per second squared. So we can get to all of these other units from our prime 3. And that's just the point I wanted to make. Also, I want to go over how powerful dimensional analysis can be. What is dimensional analysis? Well, I think if I do an example real quick, then I can get that for you. But basically, if you have an equation, the stuff on the right hand side better have the same units as the stuff on the left hand side. Otherwise we can't say they're equal. We can't have meters on the left and years on the right. We have to have meters on the left and meters on the right, or years on the left and years on the right. So what we can do, an example from another textbook I have, is show that the expression velocity is equal to acceleration times time. We'll derive this in a, I think, next class period. But show that this expression is dimensionally correct. Dimensionally correct. And what does that mean? Well, let's look at the units on the left and let's look at the units on the right. Well, I just showed you velocity is length over time. Acceleration, I showed you, was length over time squared. And we multiply it by time one more time. Cancel, cancel. We can use algebraic operators on this, and if we can add and subtract things as long as they're the same units. Multiply, it doesn't matter. We just have to make sure the units are correct, and dimensional analysis can get us there. It's bothering me. So what does this show? That we do indeed get length per unit time. So the expression velocity is equal to acceleration times time, we just verified that that will at least give us the proper units. And you can figure out what some constants of motion might be, or proportionality in this method. One more thing I think we should go over is conversion of units. How do we get from one to another? Well, you're typically given tables, or you can find tables in just about every book, or you can find a conversion on by Googling it in a second. 1 meter equals, you type that in, it'll give you a whole list of what it's equal to, or you can ask how many feet, and it'll tell you. So it's all out there at the touch of your fingers. We have the capabilities now that we didn't have before. You don't have to look in a book. But let's say they gave us something like 28 miles, and we have to convert that into meters. Well, we can say 28 miles, and let's go ahead and put that in fraction form. And we're going to have to multiply that by something else. And I go ahead and put a fraction there. And we're going to want to get rid of miles, so I put miles on the bottom. Now let's come up with some proportionality. What is, if I want it in meters, then I can use the fact that 1 mile, this is coming from a table, is equal to 1.609 kilometers. Alright, that cancels miles and miles, and we have an answer in kilometers now by multiplying 28 by 1.609. The next step would be to put it into meters, and since kilometers is supposed to cancel, let's put kilometers on the bottom of the fraction. I know that 1 kilometer equals 1,000 meters. So pull out your calculator, multiply 28 times 1.609 times 1,000, and you'll get your answer in meters. Now if you had a conversion factor on the bottom, you just divide by it. You should all be familiar with this, but as a scientist or engineer, you need to be very familiar with it. This is your life. You're not going to always be given something in meters, kilograms, and seconds. We need to know how to convert those. We could do another quick example. The number of minutes in 70 years. Well, let's start out with 70 years. Make a fraction over 1. I'm going to want to get rid of years, so I'm going to put years on the bottom. And let's make a ratio for, let's just go days to hours to minutes. So this one would be 1 year is equal to 365. We'll ignore that it's not exactly 365. And that gives us an answer in days. But we need to move that into hours. So let's put days on the bottom, and we can cancel days. 1 day is equal to 24 hours. And we can go another step further. We want hours to cancel, so put it on the bottom. 24 hours, or sorry, 1 hour is 60 minutes. And then we need to take it one step further. Nope, that's it. They wanted it in minutes. I almost took it to seconds. If we wanted it in seconds, we could go one step further and multiply by 60 again. So in this case, it's 70 times 365 times 24 times 60, and we get our answer. It's 4, I think, times 10 to the 7th scientific notation minutes. So please report your answers in scientific notation whenever it is a large magnitude, right? In general, it's a good method to report your answer in scientific notation. And I think this calculation is how many breaths you have in a lifetime at 70 years with, I think we multiply it by how many times you breathe an hour. Interesting, right? I think it comes out to 4 times 10 to the 8th breaths per lifetime. I just pulled out this one little conversion piece from the problem. Now significant figures I'll go over real quick too. When you turn in your homework, these will be important, and it'll tell you if you're a little plus or minus on your answer, and it'll give it to you right generally if you're pretty close. Once you get into chemistry and stuff, they are very brutal with the significant figures, and they may give you their own specific rules. But generally we report 3 significant figures. So an example, 3.24 times 10 to the third meters. That's 3 sig figs. Now if there was a 1 in front, I would report 1.324 because that 1 is not significant. In this class, my recommendation, and in general for engineering and physics, is to keep every single number in your calculator until you're finished, and then do any rounding. Do not round early. You'll end up with answers that are significantly different than what the solution should be. And if you're turning in something into a digital platform like Expert TA, you want to be as close as possible. So calculate, if you're calculating the sine of pi over 9, or I don't know, something that comes out weird maybe, then just put sine of pi over 9 in your expression and actually use that calculation. Don't round this off somewhere, right? Don't cut it off. Keep every single digit until your final calculation, and then report that answer with proper sig figs. I don't believe our book even has a good section on significant figures. It does. It's on page 4. It's pretty short though. Go ahead and take a look at it. Generally, we report 3. Sometimes you report 2. There's special cases. Take a look at the reading. Always read all of these sections. Don't rely on me to. You must read the book. But if you're only given 2 significant figures in your calculation, you can't report 3 back. So I can't say that 10 times 3 is equal to 30.0, right? It's equal to 30. This cannot be added unless we added some degree of precision when we were measuring, and that involves possibly having error in your measurement. Walter Lewin's first physics video, Walter, y'all need to check him out. He just passed away recently. He's an MIT instructor, and he's one of the best physics instructors out there. So you might hear me talk about some stuff that he does, because I don't know if I can do it any better. But if you're measuring something, if you had, let's just use each of these is 10 centimeters, and that's a meter long. Well, if it only measured down to an accuracy of 10 centimeters, we would report it as 1.1. So let's say we measured something that, let's say someone is laying down here, and we measure them to be, this is 1 meter right here maybe, and they're let's say they're just past the 0.1 mark. So they would be 1.1 meter long, and then we'd have to guess a little bit. We could say 1.1, it's about 3. So that gives us a level of error, and you'll learn how to work with those in different classes. We're not going to have to report any error in this class, but error and variation in data is a real thing, and once you get into your more advanced classes, you're going to have to know how to work with it. If I'm presenting some data for my research, you have a bunch of points, right? Well, you have to report the error with what's called error bars also. Your measurements are only so accurate, and a good set of data should take into account the error and standard deviations and stuff like that. All right, see you next time.